in, the before times when, we're in the class and it's kind of like, you get a couple classes in and you start to worry that nobody's going to show up, right? It's like, oh, they don't like me, right? So I appreciate you being here. It'd be a lot more boring if I was just teaching to myself over here. So I appreciate you being here. And I appreciate that people are leaving their videos on too. It helps me to be able to see your faces, because maybe it helps me sort of figure out if people, to get pacing, whether to go a little faster or a little bit slower. One of the things that I did do yesterday and this morning, I looked at the attendance poll, or not the attendance poll, but the office hour poll that I put up. And it looks like for everyone who submitted an answer to the poll, that if I keep my office hours on Monday from 12 to 1 and from 2 to 3, that I can get everybody in. So I think if you responded to the poll, everybody will fall in one of those two bins. Probably what I'll do is I'll just leave the Zoom room, this same Zoom room for the class. We can just come to this same Zoom room. And then I'll just leave it open. And if people pop in, then we can chat. But if not, that's okay too. So I'll try to put those on the calendar as well, the course calendar, so that you just have an easy link to find it there and click on the right Zoom link. So that's my plan. Right. So there's a couple of things that I wanted to go over. So homework 1 is due Monday at just before midnight. So if you want to find the homework problems, there's so if you go into content, you click on homework problems. There's 2 files that are here. Homework 1 is binned out in its own separate PDF, right? So if you click on this, you'll get like a document that's got like a snipped image of what the problem is, right? But instead of kind of recreating a document for every week, then what I just did was I put all the rest of the homework problems here in one document. So after we do homework 1, homeworks 2 through 10 will be available just in one PDF document there. So all the problems are there. So if you can get your hands, I think the textbook is useful, but if you can get your hands on an older version of the textbook, I think that the content in the textbook is very well written. There's a lot of good examples and things in there, but it hasn't changed very much, even from when I took class, 20 some odd years ago, right? So I think that's good. The other thing, we're going to talk today about thermodynamic tables, which you're going to, by the end of the class, be very familiar with, right? So if you want to find those, right? So usually we just had these online for the online exams. So if you go to content and you click on online exam materials, in here there's 2 things that you'll find. The equation sheet that we've put together. So this is all the equations basically that we think you need. If we were running in-person examinations, then these are the only 2 pieces of reference material that you would have access to. But for these online exams, they will be open book, although time limited, right? But what we're going to talk about today is these thermodynamic tables. So if you click here on thermotables, you'll get, it's a big long PDF that has basically all of these property data for materials like water and air, some solids like copper, refrigerants, because we'll talk about air conditioners, all this different stuff, right? Because what we're going to try to figure out is how much energy is in a particular bit of mass when it's at a particular temperature or pressure. So we'll start to learn about how to use these tables today. But if you want to find them, you can look in this online exam materials and then click on thermal tables. And this is a PDF. I would recommend just downloading that and keeping that somewhere, somewhere where you can access it easily, because you'll be using these tables for the majority of the problems that you do in this class. Right. The other thing that's in here is this thermodynamics equation sheet. So I put this together in like, 2015 or something, right? And basically this is, all the equations I think you need to write the final exam in this class, right? Which means all the equations that you need to write the first exam and the second exam too. So you'll see, right, the only equation that we really know so far, right, is this delta E, which is equal to delta U plus delta KE plus delta PE. That's equal to Q minus W, right? So that equation we know. Most of this stuff we haven't really seen. I guess in the preliminary information, there was some stuff about hydrostatic pressure, but that won't be on the exams. So you won't really need that. And then as we learn more and more of these in this class, more and more of this equation sheet will be kind of like opened up to you as we level up. But for now, what we know is first law for closed systems. Right? And speaking of the first law for closed systems, right? So we know that what we're trying to do is figure out what kind of energy change did we have in our system, and how was that change in our system, how did that come about, right? So did it come about because we added heat to the system, or because the system produced work, right? And we have a strategy for this now, right? So we know that there's some questions that we've got to ask. We've got to say like, okay, what's going to be in our system, right? And that's what we're going to start to look at today. But then our second question is going to be, is the system open or closed? And for now, it's closed, right? It's going to be closed until we get basically past the first midterm, right? And then what happens to our system, right? So that's this first law, right? So what's in the system, right? And then once we know what's in the system, we can start to work on this delta E term. We already have a strategy for finding work, right? Work is the integral of PdV. And then we'll use the first law most times to find this heat transfer term, right? So this is conservation of energy, or the first law of thermodynamics. We're trying to find how the energy changes in the system over time. And the two different types of energy transfer that we're generally interested in are heat transfer and work. Oftentimes, when we look at this equation, we'll neglect kinetic, potential, and spring energies, right? So when we do that, right, because remember this delta E is, delta KE, delta PE, delta SE, and delta U. Now in this class, right, because we'll often be, if you think about like the, maybe the quintessential or one of the first examples of thermodynamics, right, was this idea that we, somebody's shoveling coal into a steam engine, right, like a locomotive, and it's making the train move. Right? So this delta U, right, it'll tell us something about that water as it goes from liquid water to steam, and how much energy is stored in there, right? And how can we turn that into work, right? We know how to find work now. Work is the integral of PdV, and we did an example of that last class, right? So at least we know one strategy, although you can get different pressure-volume relationships. But this strategy is generally a good one, right? But now, right, there's three pieces of this equation, right? And last class, in order to do the problem with the first law, the problem had to tell us what Q was so that we could find delta U. But on the exam, that's probably not how we're going to do it, because what we're going to start to learn now is how do we find delta U, right? So our general strategy with the closed version of the first law will be get the pressure-volume relationship, find work. Today we're going to talk about strategies for finding delta U, and then we'll use the first law to find Q, right? So maybe the first way that we can start to think about how to find delta U is if we talk about what we call simple systems. Now, it's important to remember that simple doesn't necessarily mean easy, right? Simple means uncomplicated, right? So in these types of systems, right, we know that delta E is equal to Q minus W. So in a simple system, thermodynamically, we're talking about systems where either Q or W is equal to 0. So we can have this simple system A where there's no work. So there's only heat transfer. So then if I know the heat transfer, I can find delta U, right? Because then delta U, if we could make the assumptions that the change in kinetic and potential and spring energy is equal to 0, then delta U would be equal to Q, right? We still don't know how to find that because we don't know how to find Q, right? But if you had, if you were in year 3 or 4 and you'd taken heat transfer, then you could probably do that, right? But if we have this simple system where it's adiabatic, right? Remember, that's the fancy engineering term for perfectly insulated, meaning no heat transfer between the surroundings and the system. And we know work, right? So, or maybe we know the pressure-volume relationship, so we can say the work is the integral of PdV. In this case, because Q was equal to 0, then delta U would just be equal to negative of the work, right? That would just come from the first law, right? And then we could say, oh, work is the integral of PdV, And then we could find delta U that way, right? So right now, we know how to find delta U if, and maybe only if, it's a simple system that's adiabatic and we know the pressure-volume relationship, right? Then we could find delta U. But if we got into even a simple system like this, where there's no work, but there is heat transfer, now we're kind of in trouble because we have two unknowns and we don't know how to get either of them, right? So this is a situation you never want to be in mathematics, right, or in engineering, where you have an equation with too many unknowns, right, and not enough equations, right? So this is actually the big problem with doing things like thermodynamics and heat transfer and fluid mechanics, is that oftentimes we're really good at knowing what the equations are, but the problems tend not to be well posed when you start to look at interesting problems, because you can't solve them analytically because it's a case like this where you have too many unknowns and not enough equations, right? So today we're going to try to jump over that hurdle, at least for this equation. If we know that delta U, after we've made some assumptions, is equal to Q minus W, right? We know we can find work. I could simplify this, right? Because remember, we know that U, the total internal energy, is a extensive property. So I could make delta big U equal to mass times delta little u, right? And that would tell me something about the change in the specific internal energy, right? But that doesn't really help me unless I know what delta little u is, right? But if I could find delta little u, then I could find the heat transfer, right? I could use the first law to find the heat transfer, right? So basically this equation has kind of three unknowns. Maybe you could think about this as four unknowns because it's U2 and U1, right? We know how to find one of those things. Today we're going to start to look at how to find the change in internal energy, and then we can use the first law to find heat transfer, right? So today's lecture is really going to be about how do I find the specific internal energy in a system, or even if I can't find the specific internal energy at a particular moment in time, maybe I can find the change in the specific internal energy of the system as it moves through whatever process we're looking at. Right? So how do we measure this specific internal energy? Now, the problem is it's actually kind of tough to directly measure specific internal energy. Right? So internal energy is this energy that's associated with kind of like the motion of the molecules or the temperature or the pressure of whatever mass we're looking at. Right? So it's hard to measure this directly, right? But the good news is we don't have to. Now, if you remember, when we talked about the sort of the lectures that I asked you to watch on your own beforehand, it talked about states, right? And this idea that if you can find two independent intensive properties, right? So two properties that are not dependent on each other. So that means like if I knew the density and I knew we call it specific volume, the volume divided by the mass, then those aren't independent because one is just mass divided by volume and the other is volume divided by mass. So they're actually the same piece of information. It's just one's the reciprocal of the other, right? But if I know two independent intensive properties, then I can what we call fix the state. So if I know these two things, then I actually know everything, right? Or at least I could look anything else up in a table, right? So I talked about how to find these tables on the website, right? But what these tables are, this is a particular type of table for a superheated vapor, right? We can think of that as being steam, right? Which is important for this is kind of like, it was a little bit heartbreaking to me when I found this out, but you hear about nuclear power plants, right? And it's kind of like one of these crowning achievements of humanity is we figured out how to split the atom, right? And what did, mechanical engineers found out about this, right? And we thought, I know, I can use this to boil water, right? Because what happens when we split the atom is we create this tremendous amount of heat, right? And usually if you're a mechanical engineer, or at least historically, what we as mechanical engineers have done with I got a bunch of heat, we think, oh, that's great because I can use heat to boil water. And when water boils, it goes from liquid, which is really densely packed molecules, to steam or vapor, which is molecules really spread apart. So it wants to like expand. So if I let that steam expand over some fan blades, which is something we might call a turbine, you could think about it as like a wind turbine or a windmill, right? So we get this steam to expand, it's got some velocity and it pushes on these fan blades and it makes those fan blades spin, right? Just like in a windmill, when the wind passes by, that windmill starts to spin, right? Now I have a rotating shaft, right? So we've turned mechanical, or we turned heat energy, right? We use that heat to boil water, and then we use that steam to give us some mechanical energy, right? So we did this energy transaction. We said, oh, I can make some heat, but what I really want is mechanical energy. I want something spinning, right? But in order to try to understand that, we need to know how much energy is in the steam, right? So when we look at these tables, right, this is for steam, right? There's some things that we have to know here. If we know the pressure and the temperature, then that might let us, at least if it's steam, find any of these other things, right? So little v, this is specific volume, or the volume divided by the mass. That's like the reciprocal of density, right? You can see it's meters cubed per kilogram. We have this specific internal energy, this little u, right? That's what we're looking for in the first law, right? This is in kilojoules per kilogram. This is also an intensive property, right? Because it's energy per unit mass. We have this thing called H, which we haven't talked about yet. It's called enthalpy, right? Also in kilojoules per kilogram. And then we have this little thing called little s, which is specific entropy, which is related to the second law, which we'll get to eventually, but, you know, in a couple of weeks, right? This is in kilojoules per kilogram Kelvin, right? So here, if it was steam and I knew the temperature and the pressure, then I could find the specific internal energy on this chart, right? So if I knew it was at 100 bar or 10 megapascals and say 400 degrees, I could just run over here and see that the specific internal energy would be 2832.4 kilojoules per kilogram. All right, so what we're going to do over the next couple lectures is try to start getting familiar with these tables, right? So how do these tables work, right? So that's what we're going to try to do in the next couple of lectures, right? So we talked about states, right? Now, a state is basically what does your system look like at any particular instant in time, right? And we can fix this state based on its thermodynamic properties, right? And we said today already that we can fix this state. We can know everything about this state as long as we know two independent intensive properties, right? So we know everything about the system, about the system at a particular instant in time if we can fix the state. So if I know two independent intensive properties, then I can fix the state, right? Which means basically it's going to take some effort, but then I can go to my table and figure out, say, what the specific internal energy is, right? So when we talk about fixing a state, we need these two independent intensive properties, right? And we've talked about drawing pressure versus volume curves before, right? Now, here, if we do this as volume, this is an extensive property, but if we divided the volume by the mass, pressure is an intensive property, and then specific volume is also an intensive property. So here, what I could do, if I could, you know, define the pressure and the specific volume, in this case, this looks like an ideal gas. This might be something like an internal combustion engine, might have a cycle that looks like this, right? So a cycle is made up of several different processes. So here we started at a high pressure and a low volume, right? So that's maybe a piston at top dead center, right? With the gas compressed, and then we ignite the gas, right? And what happens is the pressure goes down and the volume increases because we're pushing that piston down, right? And then what happens is we have this exhaust process, right? And then we compress the fluid as we, you know, the piston moves back up, so the volume gets smaller and the pressure gets higher, and then we ignite the fluid, right? So we ignite the fuel that's in the fluid, and that also increases the pressure, and then we come back down, right? So that's what this could look like. So really, each one of these dots here is a state point, right? And then connecting the dots is a line that depicts a process. And one of the things we'll see that's cool is that, so at this state point, there's a particular internal energy. And at this state point, there's another particular internal energy, right? So the difference between those energies is the same, but depending on the shape of the line that you draw, you get different values for the work and the heat as you move through the process. So this is kind of neat. This is where the engineer has some control over what the thing that they're trying to design is, right? So you make a machine, and your machine will drive you along a certain path, right? And depending on what your application is, maybe you want more heat transfer, right? Or maybe you want more work. And as you make different design decisions about your system, then you'll follow a different path, and you'll get different values for those things as you move through your process, right? So this is a thing, there's all these kind of engineering definitions, right? Things like adiabatic, right? You take out your engineering decoder ring and it says, that means perfectly insulated. It's kind of funny. Sometimes I feel like, we made up all these fancy words just so we seem kind of smarter, right? So, but it's also, you do have to know these things, because people in the community, when you're talking about these things, will use these words, right? So you do have to kind of know what they mean, right? So an intensive property means a property that does not depend on mass, right? So if you have, you look at a particular depth in a swimming pool or in the ocean, every bit of mass at that depth is going to have the same pressure, right? So it doesn't matter how big a mass you're looking at, the pressure is the same, right? But volume is an extensive property, because as you have more mass, it takes up more volume, provided everything else stays the same, right? But if you looked at the density, or the specific volume, which is just 1 divided by the density, that then becomes an intensive property, right? So dependent versus independent. So dependent properties are going to be things where once you know one, you know the other, right? So the example that I gave for this is density and specific volume. So if you have the density and the specific volume, you might think, oh, this is great, I can fix the state because I have 2 intensive properties. The problem is that these properties are not independent, right? Because once you know the density, you automatically know the specific volume, because it's just 1 divided by the density, right? They're really the same piece of information, just presented in a different way. Right? So if I'm looking for independent properties, so to fix a state, I need 2 independent intensive properties, right? So pressure and specific volume. If I have these 2 things, I can always fix the state. Those are 2 independent intensive properties, right? If I have the temperature and the pressure, sometimes I can fix the state. So as long as the phase is not changing, right? So if I have liquid water and I know the temperature and the pressure, and it's not at the boiling temperature, then I can fix the state. If I have steam and I know the temperature and the pressure, then I can fix the state. But if I was making oatmeal for my kids this morning in a pot, right? A sealed pot. If I knew the temperature and the pressure, or if you think about something like a pressure cooker that's sealed, just because you know the temperature and the pressure doesn't mean you can fix the state. Because, if I told you you were at atmospheric pressure and you had water that was boiling, if you're familiar with the metric system anyway, you would know what temperature that water was at, right? And if I was familiar with the imperial system, then I would have probably also know what temperature that water is at, right? But I know that here on Earth, where the pressure is generally around 101.3 kilopascals, that water boils at 100 degrees Celsius, right? So if I know the temperature and the pressure, and those temperature and pressure are whatever the boiling temperature is at that pressure, then I can't fix the state, because I don't know how much liquid water I have, and I don't know how much steam I have, and I could have any combination of those 2 things, right? So one of the ways that we try to graphically understand this is we can plot for any given pure substance, so something that's not a combination of different substances, we can plot something that looks like this, right? This is a PVT surface, right? Or pressure, specific volume, and temperature. These are all intensive properties, right? So if I was looking at, say, something like water, I could draw something like this. So there's some combination of pressure, volume, and temperature where my water would be a solid, right? It would be ice, right? And then if I'm doing some kind of sublimation experiment in my freezer maybe, then I could have some other state where I have some combination of solid and vapor, right? So the ice would be going through some kind of a sublimation process there where it's skipping the liquid and it's going directly from being ice to vapor, right? So if you think about dry ice, which is like frozen carbon dioxide, it will go directly from ice to vapor, right? It doesn't sort of become liquid CO2 at some point, right? Now, I can also think about water as just a liquid, right? This is probably how we're most familiar with water, right? Because, conditions on Earth, generally give us liquid water, right? I could think about water that's boiling, right? Even in nature, right? If water comes close to lava or something, right? Then it'll boil, right? And I can have this dome over here where I have some combination of liquid and vapor. Right now, for us, this what we're going to call the vapor dome is pretty critical, right? Because you think about, give a mechanical engineer heat, what we want to do is boil water, at least historically, right? Because that means we can make some kind of a power plant, right? We can boil water and make something move, right? So we're actually very interested in what's going on underneath this vapor dome, right? So on this diagram, there are some single phase regions and some two-phase regions. So phase means, is it a liquid or is it a solid or is it a vapor, right? So there's some single phase regions where all of the material will be either a solid, a liquid, or a vapor, or ice, water, and steam, right? But there's also some two-phase regions like this vapor dome here where you can have water and water vapor coexisting at the same sort of instant in time. Right? So in one phase regions, you can either have solids, liquids, or gas or vapor, right? But in two phase regions, the one we're going to be most interested in this class is what we call the vapor dome, right? So under the vapor dome, water and water vapor can coexist, right? Now, if you've ever used a pressure cooker, this is exactly what your pressure cooker does, right? Because at a given pressure, you will have a given boiling temperature, right? So a pressure cooker will boil water until it gets to a particular pressure. And then once it's at that pressure, you have some coexistence of steam and water. There's also some air in there too, because you didn't vacuum it out to begin with, right? Now, here you can have steam and water coexisting for any given amount of time, provided you maintain that pressure and temperature, right? So they can exist at steady state. Steady state means things are not changing with timing or with time at that given state point, right? So if we're under the vapor dome, we can't fix our state with temperature and pressure, because with just temperature and pressure, I could be anywhere along a particular line here, because I don't know how much of my mixture is liquid water and I don't know how much is steam. So we introduced this new property that we're going to call quality. So quality is the mass fraction of vapor in a given mixture that's a two-phase mixture, right? So that we're under this vapor dome. Quality only makes sense if you're under the vapor dome, right? Because it's going to tell you what percentage of your mixture is steam versus the total mass in the system, right? So quality runs from 0 if your mixer. So, I'm making oatmeal, right? It's, my grandmother told me a watch pot never boils, right? But I'm still watching the pot, right? It's going, it gets to 100 degrees, right? But it hasn't actually started to boil yet. So the quality is 0. It's at the right temperature and pressure for boiling to happen, but boiling hasn't started yet, right? And then if I leave my pot on the stove and I forget about it, right, then I could get to a point, if it was sealed, where I boil all the water and it's only steam in there, right? But the temperature and pressure are still the same. So then the quality would be 1 there, because in my mixture, I would have only steam, right? So now we have this interface between single and two-phase regions, right? So I've sort of color-coded these. So if we have saturated liquid, right, that means that it's water, right, or liquid that's at the right temperature and pressure for boiling to happen, but it hasn't boiled yet, right? So it's liquid, but it hasn't started to boil yet, right? Similarly, saturated vapor, which is this red line over here, this is steam that's at the right temperature for boiling, but it hasn't, or maybe if you think about cooling down, right? So if you had steam and you're cooling it down, right? Now this steam is just at the right temperature where it's going to start to condense and form liquid water, but it hasn't done that yet. But it's at the right temperature and pressure, right? So then it's saturated vapor, right? So these definitions end up being important, right? So that's what they mean. So if you have a saturated liquid, then that means your quality is exactly equal to 0. And a saturated vapor is quality exactly equal to 1. Now, on this vapor dome, there's like the tip of the mountain, right? So if this is kind of like a mountain or a hill, then the highest point here we call the critical point. The critical point's kind of interesting. It's made up of some temperature and pressure, and I guess specific volume too, but we typically talk about the critical temperature and the critical pressure. This critical temperature is the maximum temperature where liquid and vapor can coexist at equilibrium, right? So if you're below this critical temperature, then you have a chance of having water and water vapor together at equilibrium or at steady state. So you could put water and water vapor together in your pressure cooker at some pressure, and part of your mixture would be steam and part of your mixture would be water. And you'd be able to keep it that way indefinitely if you had an isolated system. Similarly, the critical pressure is the highest pressure where you can have liquid and vapor exist at the same instant, right? So in equilibrium, right? So the critical pressure and the critical temperature are the temperature and the pressure that are associated with this critical point, sort of the tip of the vapor dome. If you take materials, I don't know, have you guys taken materials science yet? That's okay. So they'll often talk about things like, you know, how do you quench steam or steels, right? How do you get metals to have certain properties? And they'll look at phase diagrams like this, right? Where they flatten out the phase changes, because they're actually not really interested in the phase change as much as we are in thermodynamics. So you could take this PVT surface, right, this three-dimensional graph here, and flatten it out to a just a pressure versus temperature curve. But if you do, then you lose all the information as you're going from a liquid to a vapor, right? Because this is just a straight line, right? So it doesn't show us anything different as our quality is changing. So we won't be using this sort of projection of the PVT surface in this class, right? So that'll tell you what the saturation temperatures and pressures are, right? So the rest of this is not that. But so what we're interested in, right? Because we're mechanical engineers, right? So mechanical engineers, when you give us heat, right? At least historically, what we've wanted to do is use that heat to boil water, because as we boil that water, it becomes steam. We can force that steam through a turbine over some fan blades, and it'll make those fan blades turn, and we can use that with something like a 4-bar linkage or something to make, say, wheels on a locomotive turn, right? So this is one of the ways that we as mechanical engineers turn heat into mechanical energy, right? And for that process, what we're typically going to want to do is draw pressure versus specific volume diagrams and pressure versus temperature, or temperature versus specific volume diagrams, right? So in both of these diagrams, they're also kind of slices out of that PVT surface, but they preserve the vapor dome. So here we cut through the vapor dome so we actually see it, right? So here we can see that, I guess the big difference here, right? If you're just sketching these, they kind of look the same. They got a vapor dome in the middle. But it's important to know what a constant value of the other property is, right? So here on our PV diagram, a constant temperature starts up top left and it goes down. Then if it's under the vapor dome, it stays flat. And then it keeps going down as we move left to right. A TV diagram, we might be interested in what a constant pressure curve looks like. And it's similar, but also kind of the opposite, right? Where the pressure went down and to the right, but flat under the vapor dome. Here now a constant pressure line goes up and to the right, but constant under the vapor dome. Right, so we'll get more used to these PV and TV diagrams as we move through the process. But understanding these will help us start to be able to fix states. Because as we'll see, what we really want to know when we're talking about water is, are we talking about liquid water? Are we talking about steam? Or are we talking about some combination of those two things? Right? Because we'll see that there are different tables depending on where we are on this TV or PV diagram. Right? So ultimately, we like these graphs, right? This is one of the parts in our solution method, right? It says, draw a picture, right? Give me a schematic. And sometimes that's the schematic like we saw before of the, the piston cylinder assembly, right? And we pulled the pin and that made the piston move, right? But another schematic that we'll be looking for is a schematic like these, either a TV or a PV diagram that's plotting out where our state points happen, right? Now you won't be expected to do these things to scale, but it's a good way to try to figure out, if you have water, is it liquid water or steam or some combination, right? And we'll see over the next couple lectures that depending on where you are here, you're going to look on different tables to find that value of specific internal energy, right? And just to bring it all back, the whole reason we're talking about this is we're trying to find the specific internal energy of something like water, given that we can fix its state, right? So once I can locate a point here, right? Because every point here is a combination of two independent intensive properties, right? I guess unless I'm under the vapor dome, right? But I guess it's still a point. We know the quality, right? So once I have that point, that means I fixed the state. And if I fix the state, then I can find the specific internal energy, right? So this becomes the question, right? So let's say I can draw this sketch and I can put a point on this sketch. Now, how do I find the right table to look in so I can find specific internal energy, right? And the answer is, right, it comes back to this question, right? The first of our three questions is what's in the system? Now, this is a two-part question for something like water. Because, okay, what's in my system? Water. Okay, but is it liquid water? Or is it steam? Or is it some combination of the two? Right? And in order to answer that, I need two independent intensive properties. Right? So being able to draw these kind of graphs, right? So this is a TV diagram. This one is to scale, but don't worry, you don't have to draw it to scale. Right? So here, remember I color-coded these, right? So this is our saturated liquid line, right? This blue line. And the red line is the saturated vapor line, right? And the important thing here is that this is a TV diagram, but a PV diagram, the shape of the vapor dome looks different, but the general placement of things will be the same, right? So here, I've got the blue line up until I get to the apex of the vapor dome, right? That critical point. And then I got the red line as I continue to go down the vapor dome, right? So if I'm above the vapor dome and to the left, right? So if I'm above the blue line here, that means that I have liquid water, right? Liquid water we call either subcooled or compressed liquid. Now, if I'm looking in the tables and it's water, then that means that I look on table A5 in the table. So that tables, it's like pages and pages and pages of tables, right? So they're listed, there'll always be table A something, right? Because it's like appendix A. But the first half is all in metric, right? So there'll be table A5. And then I think what happens is the second half is imperial units, that's for sure. I think they're then labeled, I can't remember if it's AE5 or A5E, E for like English units, right? Because it was, it's even though it's America, I think is like the only place in the world that still uses them. They were developed by the English, so we can blame them for saddling us with feet and inches, right? So here, if we're above the vapor dome and to the left, this means we have liquid water, right? Liquid water is either subcooled or compressed liquid. So it's cooled enough that it's, because there's two ways you can get liquid, right? You can leave the pressure the same and cool something down, right? If you had vapor, you'd cool it down and it would condense. Or if you had steam and you really pressurize the heck out of it, right? You get liquid, right? That's how we get, if you ever seen liquid nitrogen, it's in like this torpedo looking vessel, right? Because it looks like that because it's very highly pressurized in there, right? So if you take a gas, you can compress it down. Eventually, it'll turn into a liquid. So sometimes we call this a compressed liquid. Basically, here we're liquid, right? If we're on this line, and that means you look in table A5, right? A5 will tell you about compressed liquids. If we're on this blue line, we've got some choices, right? We talked about this. This is the saturated liquid line, right? So this means that we're starting to get into that region where temperature and pressure are no longer independent, right? Because if I'm at, like I said, if we're on Earth and the pressure is atmospheric pressure, 101.3 kilopascals, we know that water boils there at 100 degrees, right? But I don't know if I have 100 degrees and 1 atmosphere, if it's all liquid, or 100 degrees, 1 atmosphere, it's all vapor, or some combination of the two. I don't know, right? But here, this saturated liquid line, I would look on the two-phase tables, which are table A2 and A3 for these lines, right? And we'll talk about two-phase stuff more next class. Now, if I'm above the vapor dome and to the right of the critical point in this red region, above the red line, this means I have steam, right? So steam we call superheated vapor, right? Because it's vapor, but it's past the critical point, right? Or not the critical point. It's past the boiling temperature at that particular pressure that you're at, right? Here, if you want to know about the properties here, you'll look on table A4. So A4 is for steam, right? Or for superheated vapor. So this is above the vapor dome, but to the right of the critical point. If we're on this red line, then we have a saturated vapor. So that means, again, the temperature and pressure are equal to whatever the saturation values are. So if you know the temperature, then you know you're at the saturation pressure. Or if you know the pressure, you know you're at the saturation temperature. Saturation temperature just means the temperature water boils at for that pressure, right? Saturation pressure means the pressure where water would be boiling if it was at that given temperature that you know, right? So that's you're on the edge of the vapor dome. Now, next class we'll talk a little bit more about this, but as we're under the vapor dome, it means we have some combination of liquid water and vapor, but they're all at the same temperature and pressure, right? Because the system won't let them get out of balance until you boil away all the water, basically. You're going to stay at that boiling temperature until all the water is kind of like sacrificed itself to become steam. So if you're here, you're under the vapor dome, you have a two-phase mixture, and you can look on table A2 or table A3. I think table A2 is better if you know the temperature, and table A3 is better if you know the pressure. Right? And we'll get into some examples of that next class. All right, so if we're under the vapor dome, because temperature and pressure are dependent, right, we need another independent property, and we talked about this value quality. Quality is the mass fraction of vapor. So what percentage of your mixture is vapor by mass, not by volume, right? And that goes from 0 all the way at the blue line across to red, or across to 1 at the red line, right? So 0 means it's all liquid, but it's ready to boil. 1 means it's all vapor and it's finished boiling. There's no more liquid left. So if you put in just a little bit more heat, that temperature is going to shoot up, right? Because there's no more water to kind of sacrifice itself to keep at that same temperature. So this is, we can imagine, like I said, I was making oatmeal today, right? And it started as liquid water in the pot, right? So we're down here, right? But I added some heat, and eventually, right? This is like when my grandmother was telling me, watch pot never boils. Doesn't look any different, right? But the temperature is going up. So I'm storing energy inside this liquid because it's hot, right? If I put my finger in it, right? Then I'll be able to tell that there's more energy in there than there was when it came out of the tap at about 4 degrees. Right? Now, this isn't exactly my oatmeal pot because here we've got a piston on top so that there's no water-air mixture, right? It's all just water, right? Then what happens is I start to boil, right? Now, as I boil, I keep adding heat, but the temperature stays the same, right? But what happens is that extra energy from the heat is breaking up those water molecules, right? Because what happens is liquid water, those water molecules like to be close together. But vapor, right, as these molecules start to bounce around a little bit more, vapor, it's like my 3-year-old when she gets super excited. You don't want to get too close because the arms are flailing around all over the place, right? So, the water vapor gets further and further apart, but the temperature stays the same. As long as we've still got some liquid water in there, the temperature stays the same, right? Now I keep adding heat, right? And eventually I'll get to this point where it's saturated water vapor, right? So that's the last 2 liquid water molecules just separated, right? So now there's nothing else, right? Because it takes a lot of energy to break those water molecules up. But once all those liquid water molecules are broken up, the vapor doesn't have much chance of remaining at the same temperature. So what happens is as your heat keeps coming in, the water vapor, the temperature shoots up really, really fast, right? This is a situation you never want to be in if you have a nuclear reactor, right? There's emergency systems that are just dumping extra coolant into the system to keep the temperature low because the temperature escalates extremely quickly, right? Once you get to this point, right? So if you're operating a system and you don't want temperature to run away, you want to stay solidly under the vapor dome, right? Now, if you keep adding heat, what happens is you get steam, but that steam we start to say now is superheated, right? So this is good if you're using your steam to run a turbine because it has more energy in it, right? So it wants to expand even more, right? So it can turn a turbine even more, right? Get you more mechanical energy. But this temperature starts to escalate very quickly, right? So it takes a lot of energy to get past this boiling temperature, but once you're past it, it shoots up quick. Right? So what we're going to talk about today, and we have just a couple slides left, right, is these single phase substances. So these ones are a little bit easier to go through. So I'm going to real quick show you how to use these tables, right? So let's say, for example, we want to find the specific volume, the specific internal energy, the specific enthalpy, and the specific entropy of water when it's 10 megapascals and 400 degrees Celsius. So what I got to figure out is, okay, 10 megapascals and 400 degrees Celsius, where am I on this curve, right? Am I liquid water? Am I steam? Or am I under the vapor dome, right? And 10 megapascals, that's a really high pressure, right? So usually we're at 100 megapascals, right? 100 kilopascals, right? So that's orders of magnitude lower than this, right? So I'd have some intuition if this was 1 atmosphere, I'd know water boils at 100 degrees. But as the pressure increases, then the boiling temperature will change, right? So I don't know if I'm boiling or not, right? So I got to look in the tables. So if I don't know where I'm going to be, I like to look at either table A2 or A3 to try to figure it out, right? So here I know the pressure. So if pressure is known, I look on A3, and if temperature is known, I look on A2, right? So here, Pressure, this is in bar, right? So bar, 10 megapascals equals 100 bar, right? Because a bar is 100 kilopascals, right? So then to get to 10 megapascals, then we get 100 bar, right? So now I look at this table, I would go down all the rows, and eventually I get to a row that says 100 bar, right? So this is the line that I'm looking at, right? So the things that I know are the temperature and the pressure. If my temperature was 100 bar and if my pressure was 100 bar and my temperature was 311.1, I wouldn't be able to answer this problem because I wouldn't have enough information to fix the state, because in that case, temperature and pressure would be dependent, right? But here, my saturation, so if the pressure is 100 bar, then water would boil at 311 degrees, right? But I'm at 400 degrees, right? So that's higher, right? So I've already boiled the water. So that means that I'm not a two-phase mixture, but it means that I must be water vapor because the temperature is higher than the temperature at which water boils for that given pressure, right? So here I know that water boils at 311, I'm at 400, so I'm past the boiling point. So I have steam, right? So I'm in table A4. So that's my next stop. Now, table A4 is actually a combination of a whole bunch of different tables, right? And at the top of all of these tables, they'll tell you a pressure, right? So I look for the subtable in A4 that has the right pressure, right? 10 megapascals is 100 bar, right? So I find my pressure, I find the right subtable, and now I look for the right temperature, right? So 400, I'm lucky 400 degrees is a row on my table, right? So now if I want all these properties, I just take, oh, here's the specific volume, here's the specific internal, like I would just read these numbers off, right? And I'd write them down and I would be finished, right? So that's good, right? I know the answer. Basically, I wrote down the information from the tables. But what would I do if the temperature here was something like 490 degrees, right? It'd be a little harder because the table doesn't have a row for 490 degrees. It's got 480 and 520, right? So what we're going to start to talk about next class too is this idea of linear interpolation, right? So if you're ever like selecting electives, right? And the elective starts with nonlinear something, right? That's like code for this class is probably going to be hard, right? But the first thing they're going to tell you, because this is a nonlinear system, if you look at like the specific internal energy as a function of temperature, it's not just a linear line. As temperature goes up, specific internal energy goes up. But the first strategy you learn to try to solve nonlinear problems is hope that your data points are close enough together, because then you just assume that it's linear between your data points and you approximate your answer, right? So what we'll do here, right, and we'll talk about this more next class, is we know from our table we have two temperatures, right? So the lower temperature and the higher temperature, we're somewhere in between these two temperatures, right? And then we have the specific internal energy that's related to that low temperature and the specific internal energy that's related to the high temperature. So you could go through and you could like define a linear equation, right? You probably did this in high school, right? Y equals mx plus b. You could do it that way, but I think it takes a lot of time to do it that way. So instead what I do is I say, okay, what's the temperature that I'm interested in, right? Like I think in the example we talked about, it was going from 480 to 520, right? So the range is 40 degrees. But if I was at 490, then I've gone 10 degrees on 40 degrees, right? So that means I've gone a quarter of the difference between these temperatures, which means I must have also gone a quarter of the distance between my specific internal energies. So we're going to define what I call an interpolation factor, right? Lowercase a here. So lowercase a is going to be the temperature you're actually interested in minus the minimum temperature in your range divided by the total range, right? The maximum temperature in your range minus the minimum temperature in your range, right? So on the table, right, this was 480 and this was 520. and T was 490, right? So 490 minus 480 is 10. 520 minus 480 is 40. I'd have 10 on 40 or 0.25, right? A quarter of the way. So then if I've gone, this interpolation factor is also true because this is a linear equation. That means if I've gone 20% of the range in temperature or 25% of the range in temperature, I've also gone 25% of the range in specific internal energy. So this is also true here, right? So the specific internal energy I'm looking for, I can use this same equation. So here I would know everything about the temperatures. I'd use that to find A. I'd put A into this equation, and then I'd use A to find U of T, right? So we'll go through examples of that next class, but that's kind of the general idea of how you do this thing that we're going to call linear interpolation. So that's all that I had for you today. If you have any questions, I'm happy to entertain them. Otherwise, you're free to go.
Have you rest your day?
Thanks, you too. Enjoy the weekend.
Thank you, Professor.
And I will see you, I guess, all on Tuesday in this kind of weird summer structure that we have.
Yep. See you on Tuesday. Have a good weekend.
Okay, you too. Bye-bye.
Bye.